Jai Hind everyone, my name is Amrita Bhatnagar. I am from CSE department of Akgec. Today I am going to explain about the deadlock handling methods. So you can see here, these are the topics or outline of this lecture. System model, deadlock characterization, methods for handling deadlocks, deadlock prevention, deadlock avoidance, deadlock deduction and recovery from the deadlock. Firstly, we should see that what is the meaning of deadlock. What is the deadlock problem actually? A set of blocked processes each holding a resource and waiting to acquire a resource held by another process in the set. Okay, what is the meaning of deadlock? For example, you have two resources, tape drives. System have two resources, tape drives, and we have two process P1 and P2. Now what happened? For example, this is the P1 and this is the P2. And we have two test drives, R1 and R2. So, in this case, R1 is allocated to the P1 and P1 is requesting for the R2. And R2 is assigned to the or allocated to the P2 and P2 is demanding for the R1. So, you can see here each process demanding another resource. One resource is held by a particular process and another resource by the demand by the another process. So, you can see here there is a cycle between these processes because nobody wants to free the resources for the other process and nobody getting the resources which is demanded. So you can see in this example also, this is again same example. We have process 1 here and this is the process 2. Process 1 is resource 1 is assigned to the process 1 and waiting for the resource 2. And again resource 2 is assigned to the process 2 and waiting for the resource 1. So, we have a cycle here and this cycle is known as a deadlock. So, this is a very major problem in the system. Deadlock should be avoided or prevented because it will reduce the overall efficiency of the system. So, this loop should be break down. This is known as a deadlock. Now, you can see here system model. Resources, we have different type of resources in our system, R1, R2 up to Rm. For example, CPU cycle, memory space, IO devices, these all are the different type of resources. And different type of resources will have different number of instances. For example, R1 is a printer. So, if we have 4 printers in our system, then what it means? R1 have 4 instances. So, number of unit available in the resources is known as a instances. Each process utilizes resources as follows. Firstly, process will request for the resource, then use for the resource and then release for the. So, these all three steps are used for the resource allocation. Process will use these 3 steps for the demanding the resource and then release the resource. Now these are the 4 major conditions for the deadlock. If these conditions met, then deadlock can be possible in your system. So, we should understand these conditions should not met in our system. For example, first one is the mutual exclusion. Only one process can use a resource at a time. Okay, this is known as a mutual exclusion. Hold and wait. In the hold and wait, a process holding at least one resource and waiting for the another resources. No preemption, a resource cannot release only voluntarily by the process holding it after that process has completed its task. So, what it means, we cannot release the resource from a particular process forcefully. It will release the resource voluntarily only. Circular wait, there exists a set P0, P1 up to Pn of the waiting processes. That P0 is waiting for the resource that is held by P1. For example, P1 is waiting for the P2, P2 is waiting for the P3 and again P3 is waiting for the P1. So, this is known as a circular weight. So these are the 4 conditions. If it satisfied in the system, then there is more chances of the deadlock in the system. So we should avoid these conditions. Resource allocation graph. Now, what is the use of resource allocation graph? Basically, firstly, we have to find out the deadlock deduction. Deadlock deduction, for the deadlock deduction, we will use resource allocation. Firstly, we will find out there is a deadlock in the system or not. If the deadlock is deducted, then we will apply different handling methods of the deadlock. For example, you can see in the resource allocation, this is again a simple type of resource graph where we have vertices V and set of edges E. V is partitioned into 2 types because we have 2 type of vertices. First one is the process. Here for the process we will use this convention, and for the resource we will use here this convention R1, R2, R3. These all are the resources. Now next is the request edge. If a particular process is requesting for the resource, then we will draw a arrow towards the resource. Another edge is known as a assignment edge, which is known as a direct edge also. So in this case, if the resource is assigned to a particular process, then arrow will be drawn from the resource to the process. It means this is an assignment edge. What it means, this resource is assigned to this process. And in this case, this process is requesting for this resource. So these 2 type of edges are possible in the resource allocation graph. We have 2 type of nodes here, process and resources, and 2 type of edges will be there. First one is a request edge and another one is the assignment edge. These all are the convention which I have discussed. This is for the process, this is for the resources, and you can see here these 4 elements shows that we have 4 instances of this resource. Now PI request for the instance RJ, then we will use this convention. This is for the request edge and this is for the allocation edge. Now you can see here, this is the allocation graph where we have P1, P2, P3, 3 processes are there. We have 3 resources are there, 4 resources are there, and these arrows are showing the assignment and assignment edge and the allocation edges. But you can see here we don't have deadlock here because there is no cycle. You can see here this is not a cycle. If we find out the cycle in the resource graph, what it means? It means deadlock deducted. It means there is a deadlock, possibility of deadlock. You can see here. Now again we have another graph where we have one more edge from the P3 to R2. Now you can see we have a cycle. You can see here there is a cycle in the system. If there is a cycle, then there is a chances of the deadlock in the system. Now the another case, but there is also possibility if there is a cycle, but we don't have any deadlock. You can see here there is a cycle. You can see here this is another example, and we have here multiple resources or multiple instances of a particular resource. So you can say this resources is allocated to the P4. If the P4 release this resources, then it is easily allocated to the P3. Then this cycle will be resolved. So you can see that in this case we have cycle, but we don't have deadlock here. So there is a cycle, but no, there will be no deadlock. So we should define this thing. So you can see that these are the basic facts. Firstly, we should understand if a graph contains no cycle, it means no deadlock. If a graph contains a cycle, then if only one instance per resource, if we have only one instance, for example, this is the case, all the resources have only one instance, then the meaning of the cycle is always deadlock. Then confirm there is a deadlock in the system. But if we have several instances in the resources, then it will be a possibility of the deadlock. In this case, cycle will not a confirmation of the deadlock. It can be a deadlock or it cannot be a deadlock. Okay. Now, methods for handling deadlock. Now, we have deduct that we have deadlock in the system. Now, how we can handle this deadlock? So, first condition is ensure that the system will never enter a deadlock state. So, we have to prevent this condition. We have to prevent. How we can prevent this condition? We should not met all the necessary condition of the deadlock, or we should avoid the deadlock. So, there can be two possibility here. We can use deadlock prevention or deadlock avoidance cases. Second, allow the system to enter a deadlock state and then recover. If the second case, if we have a deadlock, we have detected a deadlock state, then we can recover it. The second possibility is there. And last one, we can ignore the problem and pretend that deadlocks never occur in the system used by the operating system, including Unix. So, in this case, we will ignore the problem. We will not handle deadlock. We will just shut down the system or switch on the system, and we will ignore this problem. Now, so firstly, deadlock ignorance, deadlock prevention, deadlock avoidance, and deadlock recovery. These are all the main methods for the handling deadlocks. Now, deadlock, how we can prevent the deadlock in the system? So, we have to eliminate the main condition of the deadlock. We have already seen that there are 4 necessary conditions for the deadlock. So, we will avoid these conditions, or we will eliminate this condition in the system. For example, first one is the eliminate mutual exclusion. So, we will have now shareable resources also there. In the case of deadlock, we don't have any shareable resources. Eliminate hold and wait condition. Must guarantee that whenever a process requests a resource, it does not hold any other resources. So, no process can hold and wait. If it wants to request another resource, it should not hold any other resources. So, it have to release all the resources previously, then it will get the another, it can demand the another resource. This is known as the elimination of hold and wait condition. Eliminate no preemption. So, we can preempt the processes for the resources. So, we can take forcefully resources from the processes, so that deadlock can be avoided by the help of this condition. Okay, if a particular resource, if the process is waiting for a long time, then we can take resources from the process, and we can complete another process which require these resources also. Eliminate circular wait. In this case, we have to eliminate circular wait. To eliminate this circular wait, we have to give ordering to the resources. For example, R1, R2, R3, R4, and in this ordering only, increasing ordering only, the system can demand for the resources. If a particular process already demand resource number 2, then now it will demand for the 3 or 4, not for the 1. It cannot request for the resource 1 now, because it can only demand for the in the increasing order only. So, this is known as a eliminate circular wait. So, in this way, by the help of this process, we can eliminate circular wait. So, these all conditions will be eliminated from in the case of deadlock prevention. Fine. The next method is the deadlock avoidance. In the deadlock avoidance, we will have prior knowledge of the resources. Each and every process should know that how many resources are required in the system. Firstly, and the second thing is, in this case, we have 2 states, safe and unsafe state. If the system in the safe state, what it means, there will be no deadlock. But if the system is in the unsafe state, then there is a possibility of deadlock. So we have to try to keep our system in the safe state. So, we can see here, if the system is in safe state, no deadlocks will be there. If a system is in unsafe state, possibility of deadlock is there. Avoidance, what is the use of avoidance here? Because we will use deadlock avoidance to keep our system into safe state. Ensure that system will never enter a unsafe state. So, you can see here, there is a safe and unsafe states are there. If you can say in the unsafe state, we have deadlock, and in the safe state, we don't have any deadlock. So how we can find out safe state? We will use different type of algorithm to find out the safe allocation of the resources. So that safe sequence of the resources allocation, so that system should be in the safe state. So banker algorithm is majorly used for the find out the safe system in the system. So with the help of banker algorithm, we can allocate the resources, because in the deadlock avoidance we emphasize on the resource allocations only. If the resource allocation is proper, then system will be in the safe sequence, safe state. So banker algorithm will help here to allocate the resources in the safe sequence. Now next is the resource allocation graph. So again we have another here in this case you can see here claim age. Claim age will find out or predict that if there is a possibility of deadlock or not. The claim age indicate that process Pj may request resource Rj represented by a dash line. So this is represented by the dash line. Claim age converts to request age when process requests a resource. When a resource is released by the process, assignment age converts to a claim age. Resource must be claimed a priori in the system. So you can see here this is a diagram where we have one allocation. R1 is allocated to the P1, P2 is requesting for the R1, and we have two claim ages. In the future, P1 and P2 can demand for the R2. So this scenario we can show by the help of claim age, and this claim age is represented by the dotted lines. If any process demands the R2, then this line will be converted into solid line. And for example, P2 demand for the R2 in the future. Then this line will be converted into R2. So if this R2 will be allocated to the P2, then you will see here. This resource is allocated to the P2, then there will be more chances of deadlock here. If P1 also demand for the R2, then there is a chances of deadlock. So with the help of claim age, we can predict that there will be a possibility of the deadlock or not. So in this case, you can see if the P1 will demand for the R2, in this case, deadlock can be possible. So this claim age will be helpful for the, we can find out the unsafe state in the resource allocation graph with the help of resource allocation graph. Now, deadlock deduction and recovery. So firstly, we will we can find out or deduct the deadlock by the help of resource allocation graph. Okay, and if we find out and deduct the deadlock in the system, then we will apply some recovery algorithms here. You can see a deduction. We have two methods: single instance and multiple instance. If the case in the resource allocation graph, if we are using single instance, then if and cycle is deducted, what it means? It means we have deadlock here. But if we have multiple instance, then we will apply safety algorithm like banker algorithms to find out the safe state or to find out the deadlocks. So banker algorithm is majorly used for the find out the deadlock, or you can say deadlock deduction, and to find out the safe sequence of the resources allocation. So that if we find out the safe sequence of the allocation, then we don't have deadlock. But if we don't find out the safe sequence of the resource allocation, then we have deadlock. So with the help of banker algorithm, we can find out the deadlock in the multiple instances resources. Okay. Now you can see here resource allocation graph and wait for graph. We are familiar with the resource allocation graph. This is a graph between the different type of vertices like process and resources, and we have different type of edges here. Now if we remove the resources from the resource allocation graph and there is only the process, graph will be same, but we have only the processes here. and we have removed all the resources from here, then it is known as a wait for graph. This is another method to find out the deadlock in the system. If we have any cycle in the wait for graph, then again there will be chances of deadlock in the system. Now, if we deduct the deadlock in the system, now the process of recovery will be started. What are the deadlock recovery processes are? Firstly, kill a process. We can kill a particular process, or if we are find out a particular cycle in the system, then we can kill a process. If the one process will kill, then this cycle will be break down and deadlock will be removed from the system. Or another process is we can kill all the process. If we kill all the process, then again system will be recover from the deadlock. But it is very serious problem, and it have many losses of the, because it is not efficient process. Okay, so we will use more mainly to this technique where we will kill a particular process only. Now the question is, which process will be killed? It can be dependent on the priority of the process, how long process has been computed, and how much longer to complete. For example, if a process is completed 80%, then this process will not be killed. If a process is completed only 20%, then there is a more chances to kill this type of processes. How many resources the process has used, how many resources process needs to be to complete. So these are the criteria by which we can find out which process can be terminated, so that we have very less amount of losses. Okay, so this is the part of your deadlock recovery. Thank you.